In the last two lessons, we looked at different aspects of graphical analysis. In lesson 1.4, we looked at nonlinear proportions and how they can be made linear in order to find an equation in the form y equals mx plus b. In lesson 1.5, we looked at how to deal with uncertainties in linear relationships by finding the max-min lines to find the uncertainties in the slope and y-intercepts. In this lesson, we're going to combine those two concepts together to look at uncertainties in nonlinear proportions. The example that we're going to use to demonstrate this concept is from an experiment looking at how the intensity of a sound varies as the distance from its source increases. So the data we're going to use is over here in this table, and it's been input, as well as uncertainties have also been input, which you can see when you double click and look at the options. So the uncertainties for D is plus or minus 0.1, and the uncertainties for I is 0.05. And so when they were graphed, you can see the uncertainty bars. And then a power regression was carried out, and the results definitely show that it's an inverse square relationship with a b value of very close to -2. And so that means in order to create a linear graph, we're going to have to create a column that raises the distance values to the power of -2. The way we do this is we go under Data and look for a new calculated column. And this new calculated column is going to be the distance raised to the power of -2. With a short name of D to the power of -2. And since distance has a unit of meters, then the unit for this column is going to be meters to the power of -2. Now the way this is calculated is by selecting the column that we want to raise to the power, which is the distance column, and we're going to raise it to the exponent, the shift 6 of -2. And we click Done, and we get a new column. This new column shows D raised to the power of -2. It takes every single one of the D values, raises it to the power of -2. Now we want to graph this, so we want to insert a graph, and on this graph we're going to change the distance to the new column, which is distance to the power of -2. And then if we click over here, it realigns the data so that it's a linear graph. Now there's one thing that's missing from this analysis, which is that the uncertainty for D to the -2 hasn't been included in the analysis. You can't simply use the uncertainties from the D column for the D to the -2. It's more complicated than that. As we talked about in a previous video, when you raise a measurement with an uncertainty to an exponent, you need to multiply the relative uncertainty of the measurement by the exponent. So in the example below, 2.5 plus or minus 0.1, first thing we need to do is figure out the relative uncertainty by dividing 0.1 by 2.5. We get 4%. Then you raise the 2.5 to the power of 2, you get 6.25. Then, when you multiply 4 by 2, you get 8%. Then, to bring it back to an absolute uncertainty, you multiply the 8% by 6.25 and get an answer of 0.5. So when we look back at our data and we try and raise our D values to the exponent of -2, we also have to deal with the plus or minus 0.1 uncertainty. So the first thing we need to do is convert that uncertainty into a relative uncertainty. We do this by dividing our 0.1 uncertainty by each of the d values. Then, because we're raising it to the exponent of -2, we multiply each of these values by 2. Now we have the relative uncertainty for d to the power of -2, which we can then convert to an absolute uncertainty by multiplying our relative uncertainty for d to the -2 by each of the d to the -2 values. All these columns can be combined into a single calculation using the formula shown below, where we take twice column 3, which is 0.1 divided by d, and multiply that by column 4, which is d to the -2. Having a single formula makes it simpler when we go into Logger Pro to graph this information. So now we can go back to Logger Pro and add the proper uncertainties onto the horizontal axis. First thing we need to do is we need to create our calculated column. Okay, and I copied the formula over just so that it would be easier to do. So this is going to be the uncertainties of d to the -2. And the units again are going to be meters to the -2. Okay, now the way we calculate it is going to be 2 times 0.1 divided by the distance column multiplied by the distance to the -2 column, just like our formula says up here. Next we have to assign these uncertainty values to the d to the -2 column. So we double click on the d to the -2 column, we go to options, and we want the error bars to be a column. That new column that we just added, the uncertainties of d to the -2. And now we have uncertainty bars on the horizontal as well as the vertical axis. The rest of the process for figuring out the relationship between the two variables, including the uncertainties, is very similar to the process that I took you through in lesson 1.5. So I'm just going to briefly show you the calculations. First, we calculated the slope and the y-intercept for the max line and the min line. Then we found the average gradient and y-intercepts and the uncertainties of the gradient and y-intercepts and combined those together into a formula in the form y equals mx plus b, where m and b both have uncertainty values. But the thing is that the y and the x in this formula are really the intensity I and the distance to the -2. This means that the actual relationship between the intensity of the sound and the distance from the source of the sound has been shown to be the equation above. I have a few notes about this relationship that could be helpful when you're writing up your lab reports and making conclusions. The I-intercept, the b value, 0.04 plus or minus 0.05, includes the possibility of it being a 0. Which means that it's possible that the intensity is proportional to d to the -2. If it didn't include the origin, then we might have considered a different type of relationship, or possibly there could be some kind of systematic error in the experiment. Also, the uncertainty on the slope is quite large, partly because of the very large uncertainty on one of the data points. This brings into question the wisdom of just using the first and last data points in order to find the max and min lines that best fit. Because the max and min lines that best fit probably don't pass through all of the error bars because of this large uncertainty. And so maybe if we use some more complex analysis that uses all of the data points, we might come up with a more valid uncertainty for the slope of the equation.